Hey guys, we still have a couple of minutes before things get started. So you guys in the meantime can think about these brain exercises. And I'm doing okay, Ashley. Thanks for asking. I'm feeling like I'm having a Monday, even though it's a Wednesday, to be honest, but that's okay. That's just how it goes. Some days you win and some days you don't win. It's not a winning day, but that's okay. And it's okay. All right, we've already got people answering the squiggly line. So somebody's got a question about the squiggly line over here. So this is a way of three-dimensionally, overall this molecule is represented in a three-dimensional way. You can see the wedges coming towards you guys. So you guys learned about wedges. So we're kind of trying to look at this molecule from the side. And you can see how, like, for example, this oxygen's kind of pointing up and that oxygen's kind of pointing down. This squiggly line here means that the oxygen can be up or it can be down, and it in fact exists in both directions. And yes, that's glucose. Good job. Yeah, that is glucose on the far right over here. Someone's asked, don't hydrogen bonds break in water? So this is a very philosophically challenging question to answer. Hydrogen bonds aren't like real bonds, right? So they're an association, but they're not actually sharing electrons between them. They're more of an association. So hydrogen bonds occur between two molecules that have a polarized H on part of a polarized bond, and another molecule that has some lone pairs. So water itself has this huge hydrogen bonding network. And when you put a different molecule into there, some of the water's hydrogen bonds with each other will break in order to make some new hydrogen bonds with whatever this new molecule is. For example, glucose will be able to get in there and be part of the hydrogen bonding network. So hydrogen bonds happen in water, and they may break to accommodate other molecules coming in, but I don't know if that helped to answer your question. Okay, so we're officially on the clock now, so let's go ahead and get started. So to start off with, people have been kind of putting up different guesses, but the far right, this molecule here on the far right, which is glucose, is the most likely to dissolve in water. So the rationale that we can use to explain that is because all of these OH bonds here are highly polarized. So there's polar groups all around this molecule, decorating it all the way around. And it's got another strongly polar interaction spot right here on the oxygen within the ring. So each one of those oxygens and each one of the hydrogens attached to the oxygen, all of those can participate in hydrogen bonds, as can the water molecules, right? So both of these other molecules also have OH bonds, and so they can also interact with water and form hydrogen bonds with water. But we have to think about the molecule as a whole, right? So in the case of this molecule in the center here, this is the easiest one to see. After you get away from this OH group here, which is highly polar, this long carbon chain here, which is just full of CH bonds, which we know CH bonds are non-polar bonds. This whole non-polar tail of this molecule is going to not be preferring to interact with the water, right? Because this side of the molecule is really only capable of van der Waals interactions. And so you can think about the slides that we saw last time in our last class, where the water molecules are highly polarized. And so they're too strongly polarized to help stabilize this side of the molecule. They'll still interact with this side. And I actually don't know the answer as to whether or not this molecule is called hexanol. You guys don't need to know that. I don't know the answer as to whether or not, I imagine that it is slightly soluble in water, but perhaps not fully. It has kind of a long chain out here, so it might actually create two phases. It might be biphasic if you try to put them together. What about this molecule on the left? What do we think about that molecule? Oh, it sits right in the middle. So it does dissolve in water. The OH group is a dominating factor of the overall molecular characteristics of this molecule. It does have a little bit of a nonpolar side to it also, but that side is pretty small, it's pretty compact, and so this molecule is absolutely fully soluble in water. Does anyone know what that molecule is? You'll get to know it before the end of the course. You don't need to know it right now, but this is actually isopropanol, which is rubbing alcohol. Here's a line angle formula question for you guys. How many carbons are in this molecule?
3.
Okay, cool. How many hydrogens?
8. Sorry, 7.
7, 8, 9. I see and hear a bunch of different answers.
8. 8, yeah, 8.
We got a 6, 7, 8, 9, and I hear kind of a consensus coming around 8. 8 is the correct answer. There's 3 hydrogens over here and 3 hydrogens over here, so that makes 6. You can see number 7, but number 8 is kind of tricky. This carbon here, which has 3 bonds, in order to have a full octet, it has a 4th hydrogen, a 4th bond there that goes to an implied hydrogen. So yeah, 8. Okay. All right. Today we're done with polarity. So that brain teaser was just a reminder of where we were, but not where we're going. Where we're going is acid and base. And yes, so the answer in the chat box, yes, the carbons over here, these carbons each have 3 hydrogens, because we can tell, since there's no formal charge and there's no other indicator on here, we can tell each of these carbons has a full octet, meaning it should have 4 bonds in this case. And so 3 of those bonds are invisible to us right now, but that doesn't mean they're not there. They are implied hydrogens. Okay, so I'm canceling my office hours again today. I actually have a deadline that I'm trying to meet. And so I want to be able to give you guys my full attention during office hours. But I know I've canceled Monday and Wednesday. I'm going to make myself available to you guys tomorrow afternoon and Friday afternoon. And I will open up so you guys will be able to see your quiz answers before my office hours on Thursday. Also, I think I forgot to put a sign up here. But there is an SI session today at 5. So I really strongly encourage you guys to go and make use of these SI sessions. It's a great time to practice. It's a great time to get personal attention and kind of help have somebody nudge you in the right direction if you're going off track, or build you up the confidence if you are on the right track. Someone asked about Zoom. My office hours are on Zoom. I believe that today's SI session is in HIBS 118, I believe. So, okay. Other announcements. You guys took your quiz on chapter 1, and I promised you on Monday that I would talk a little bit about the quiz today. And so that is what I'm going to do. I'm going to take a couple of minutes to talk about the quiz. I have heard all of you who have expressed concern to me via email. I know that the periodic table link was not working. I am sorry about that. I will get that fixed for the next time. And I'm thinking about ways to kind of offset whatever trauma that caused in terms of both your functionality during the quiz and also in the aftermath. So I haven't come up with a plan yet, but rest assured I'm thinking about a plan to counteract those technical issues. The concerns about timing, however, I need for you guys to be thinking about this in a global and a holistic sense. There will come a time when we're not online and we're not in Zoom format, and you will have to take all of your quizzes and tests during the class period, during the time allotted. And so there, as much as, every educator would like to say the most important thing is that you know the material and timing doesn't really matter. That's not actually the way it works in real life. Timing does matter. And if you think about it, the time constraint also tells me something about how well you know the material, right? You could have a week to write a paper, or you could have a day to write a paper. And if you can get your thoughts organized more quickly because you've read the whole book already, then a day might be enough. But if you haven't read the book, then you're going to need that whole week. So just keep that in mind regarding timing of the quizzes. That being said, I do want you guys all to have your best chance to show me how good you can do. So I will be having the quizzes take a little bit more time. I will give you guys another little bit of extra time, but without increasing the number of questions. But just keep in mind that there does have to be a finite limitation. And in order to really do well on these quizzes, you actually have to make sure that you've done kind of enough prep work to be comfortable answering questions quickly. And I know this time the periodic table wasn't available, and that caused a whole set of problems and a whole mess of timing issues as well. But that's what I want to say about that. The next topic that I have to talk about, I'm not really excited about talking about it, but I'm just going to rip off the Band-Aid, and here we go. If you guys are posting questions from my quizzes on GroupMe, please know that that is a major honor code violation. I heard that somebody was doing this. I heard other people were responding to it. I don't have a good way to assess whether or not you guys are cheating on quizzes while they're in progress. But what I can tell you is you should not be logged into GroupMe during a quiz. You should log out of GroupMe prior to opening the quiz, prior to opening the test. Don't put yourself in a vulnerable situation. I firmly believe that you guys who are cheating are only cheating yourselves, because when it comes time to, try to pass or go 2, you're not going to know this material. When it comes time to try to take the MCATs, you're not going to know this material. So you are hurting yourself by cheating, but you are also putting the rest of your classmates in a very sticky situation where they're not sure what to do. Do they share that knowledge that they know about? Do they not share that knowledge that they know about? So please, you guys, please pay attention to the professionalism that we expect from you guys as university students. Please respect the honor code. Please abide by the honor code, and please don't put me or your classmates in situations where we have to take action because there are honor code violations running rampant. We're all adults here, and we all need to take responsibility for ourselves. And I'm going to stop talking about that now, but hopefully that will address the issue. Just please, you guys, don't put me in the situation where I have to try to figure out who and what and when and report honor code violations, because they will be prosecuted. Okay, wipe off that topic, fresh start. You guys haven't achieved homework for chapter 2, due on Monday morning. I will finish chapter 2 on Friday. If not, I won't quite finish today, but we'll get through the bulk of chapter 2. By the end of today, you guys will have 80 to 90% of chapter 2 under your belts. And so I really encourage you to take an early stab at this homework, because on Friday, I will be assigning you a chapter 3 homework, because we're going to start chapter 3 on Friday. So the reason that we're going to start chapter 3 on Friday is because, we're going to be done with chapter 2, but also because you have an exam coming next week. Now, it was listed on the syllabus as Monday, February 14th. We are a little bit behind schedule, so I'm pushing the exam back to be on Friday, February 18th. It's still going to cover chapters 1 through 3. So we're going to start on chapter 3 on Friday. We'll cover most of the ground of chapter 3 on Monday and a little bit on Wednesday. If we don't make it all the way through chapter 3, we are still having the exam on Friday. I will be clear if that situation occurs. I will be clear about where the cutoff is of what will and won't be on the exam at that time. So what we're going to do for this exam is I'm going to give you guys a window that includes our class time together on Friday. So it'll be 24 or 36 hours. It will include the hour that the 50 minutes of our class time here. And you can take it at any point during that window, but it has to be, taken within that window. I'll be more clear about what that window is coming up. It'll either begin on Thursday morning and close on Friday night, or it'll begin on Friday morning and close on Saturday night. So I may poll you guys. I am not sure. I need to look at my own schedule and when I can write the exam. So stay tuned for when the exact window is, but it will absolutely for sure include the full day of Friday, February 18th. Okay, in terms of the format, it's going to be mostly multiple choice and some fill in the blanks, so similar to the quiz that you saw already, but also it will have some free response questions. And so because of this, because I want to be able to do both multiple choice and fill in the blank, but also free response, I have to deliver this exam in 2 parts. So the first part is going to be similar to the quiz, and it is going to require the Respondus lockdown browser. And yes, you guys will have to do a practice lockdown browser test, a practice lockdown browser assignment that'll be part of your participation credit that I'll make sure that we have to do before the exam starts so that when the real exam works, nobody will be running into technical issues. Okay, I'll probably release that assignment, a Respondus assignment on Friday so that you guys have enough time to download and test your Respondus. And then the other formatting thing I want to touch on is that, like I said, it'll be 2 parts. The second part is going to be free response, so free drawing, where you will have to draw out on your own paper, take a picture with your phone, scan it, whatever you want, and then upload it into Canvas directly. And because of the upload, Respondus does not let you upload, so part 2 will not be on Respondus. Okay. So, basically, whatever format you want to use to do the free response is fine. You can do a screenshot, you can take a picture with your phone, any of these things are fine. We are going to practice the lockdown browser, so hopefully there won't be a situation if the lockdown browser does not work. But if you're in a testing situation and you have any technical difficulties ever, you need to email me immediately. If it's part that has some kind of an upload, you need to email me with your attachment. And I will encourage you guys all to go read your syllabus about these testing questions, because a lot of these are answered there. And regarding how to log in to Respondus, the way that I've always done it that's worked for me on my end is that I would log on to Respondus first, and then from within Respondus, open Canvas. Okay, all right. I'm going to pause on the questions for now because we need to get to the rest of the science for today. But if you guys have additional format questions, we can address it next class or via email. Okay, so here's where we are in the chapter. We're more than halfway through. I'm hoping to cover the rest of acids and bases today. Probably won't make it all the way quite through the end of acidity trends, but we will at least get started on it. On Friday, we'll finish up chapter 2 and start chapter 3. And in order to be able to do that, I need you guys to, like I said last class, read about these topics on your own before Friday. I will touch on them very briefly on Friday, but these organic functional groups, there's not really anything that I can say that your book can't, and you really don't need me to understand them. So just take a look at your book. Okay, so when we left each other on Monday, we had finished up talking about Arrhenius acids and bases, which, as you remember, I'm sure, are acids and bases that dissociate in water. And those are actually just a very specific type of Bronsted-Lowry acids and bases. We didn't quite make it over the hump to getting into talking about Bronsted-Lowry acids and bases before. but we're going to do that today. And then I'm going to hop over Lewis acids and talk about these other things. We'll come back to talking about Lewis acids when we talk about the curved arrow formalism, which probably won't be until Friday. But to start, we're going to start with Bronsted-Lowry acids and bases. So here is the same slide as what I showed you guys on Monday. I gave you kind of the lay of the land with respect to these three types of acid bases. And again, reminded you guys that Arrhenius is a type of Bronsted-Lowry acids or base, because you can see these top two both deal with what's happening with the proton, right? Bronsted-Lowry acids and bases are proton donors and proton acceptors, and Arrhenius acids and bases are just the version of Bronsted-Lowry acids and bases that are interacting with water to do that donation or accepting of protons. Okay. As I mentioned also on Monday, these Bronsted acids and bases are going to be the main players for organic chemistry, and so we'll talk mostly about those. And again, I interchangeably use Bronsted-Lowry acids and bases versus just Bronsted acids and bases. Okay, so let's dig into this a little bit deeper. When I'm talking about Bronsted acids and bases, everything that I'm talking about, all of the questions are going to be about what happens with the proton. Where's the proton going? Where's the proton going to end up? Which molecule is more stable without having a proton? This type of way of thinking about acids and bases is going to be the most common thing that chemists are talking about if they just use acid or base and don't give it any kind of a designation. Okay, so here's an example of a Bronsted-Lowry acid base. If we have HBr interacting with water, that HBr is going to give up a proton to the water. So you can see in the reaction overall, the proton from HBr is going to end up on the water molecule, and Br is going to be left as Br minus. Now keep in mind, we're talking about protons, so just a proton, H plus, without any electrons moving, just the proton part. So this situation is fairly obvious that HBr is going to be the acid here that's giving up a proton, so it's donating that proton. And water here is going to be the base. What about this situation down here where we have ammonia interacting with water? Well, if we look at what happens in the equation here, the ammonia is going to gain a proton. The ammonia is becoming ammonium or NH4 plus. And that proton is coming from the water. So in this case, the water is acting as an acid. The ammonia is acting as a base. So you can think about it two ways. You can think about it as the water molecule giving up a proton to the base, or you can think about it as the base reaching out and grabbing a proton from the water. So I also want to point out here, we've got two different equations. Both of them have water in them. And in one case, the water is acting as a base to accept a proton and make H3O plus. In the other, water is acting as an acid to give a proton, leaving behind an OH minus. So water can act either as an acid or a base. And it's not the only molecule that can do that. A lot of different molecules can do that. So with these definitions in mind, I wanted to show you just a couple more examples. Here is sulfuric acid, which is a proton in the presence of ammonia. And we can see here clearly, so you can follow the activity of this pink proton here and see that after this reaction, it ends up on the nitrogen. So that makes sulfuric acid here the acid and ammonia the base. And we can see other examples of this as well, where we have a proton donor and some molecule that is able to take on another proton, right? So in this case, in the middle here, the pi electrons actually they kind of give up their nature as pi electrons and free themselves up to create a new bond with that proton. So in each of these cases here, in ammonia, in this double bond in the middle, and in this nitrogen over here, all three of these bases or proton acceptors, they have the capacity to use some of their electrons to form a new bond with hydrogen. So it's the lone pair electrons here in ammonia, it's the pi electrons here in this double bond, and it's the lone pair of this nitrogen in this C double bond N compound. You can see that in each case, we have a deprotonated form of our acid left behind and a protonated form of whatever our base was. And notice also, I didn't point this out on the last slide, but notice that we have two neutral molecules coming together. And what we're getting out is one molecule that carries a negative formal charge and one molecule that carries a formal positive charge. And it's not where the hydrogen is, it's actually on the carbon next door, or in the cases of a lone pair being used to accept that hydrogen, it's on the atom that bonded to the hydrogen. But what I want you to kind of notice here is that if your overall system is neutral to start out with, then your overall system still has to be neutral. So we have a positive formal charge here and a negative formal charge here. And so they're canceling each other out. Now, it won't always be neutral going to one positive and one negative. So I'm not saying that. What I'm saying is that the formal charges all have to add up to something on one side of the equation. They can't overall, the total charge of the overall system can't change on the other side of the equation. Does that make sense? Okay. All right. Someone has asked in the chat box, what do the different sizes of arrows mean? This is an indicator of, so these are equilibrium arrows, and these sizes actually indicate which way the equilibrium favors. So in this top case, the products here are favored, meaning that this is a strong acid and a strong base, and this reaction goes very far in this direction. In this middle case, it's not as far in this direction, so the equilibrium actually lies with the reactants in this case. And we'll see some more of that when we get into pKa in like five-ish slides from now. Okay. Again, Bronsted-Lowry acids and bases are the most common types of acid-base type things that we talk about when we as chemists talk about them. Yeah, John, you have a question?
I just have a quick question for the HCl reaction. Would you always predict that the proton would go on that left carbon?
All right. John, your question will be answered as part of chapter 6 or 7.
Okay. Sorry. Thank you.
So, yes, the answer is yes. And we'll get into this in more detail. You guys do not need to worry about this right now, but just to satisfy curiosities out there, you think about what's left behind. So when you make this new carbon-hydrogen bond, you're having to leave behind a positive formal charge. And so you have to put that proton on one of these two carbons, right? And whichever one you don't put it on will be left with an empty p orbital and a formal charge. And so we'll learn a little bit later, actually it might be chapter 3, I don't know. We'll learn a little bit later, not in this chapter, we'll learn that this carbon is better at holding that positive charge because of the carbon over here. But you guys don't need to know that right now. Okay, Bronsted-Lowry acids and bases. This is the same reaction I showed you guys a couple of slides ago, and I want to use it to introduce some new terminology that I think most of you guys have heard before based on answers that I got out of my in-person live class this morning. You guys hopefully have heard of conjugate base, conjugate acid. What this means is that for every acid-base reaction, if you have your acid and your base interacting together, then you're going to have, in the case of your acid, after it donates that proton, what's going to be left behind is a base, right? And that should make sense. If an acid has a proton that it can give up, after it gives up that proton, it's no longer an acid, it's a base. Likewise, the base, after it accepts a proton, is going to have this extra proton on it, so it's going to become what's called a conjugate acid. So one thing that I want to kind of take a moment to say here is that, of course, every acid-base reaction has to involve a proton transfer, and every single one of them is going to have two conjugate acid-base pairs. So what I mean by that is that one pair is the acid HBr with its conjugate base Br minus, and the other is the base water with its conjugate acid H3O plus. So acid-base chemistry, it is easy to get yourself overwhelmed and confused. There's a pair here with HBr and Br minus, but you also have to think about the pair of molecules that are reacting together, right? And the pair of molecules reacting over here. So I know it gets confusing. The best advice I have for you guys is to just try to keep it calm, take it slow, rationalize and use logic to work through step by step. What are you looking for? And these concepts will come more clearly over the next few slides. And someone asked a question on the last slide that kind of leads me into this. Acid-base reactions are equilibrium reactions, so we need to think about them in both directions. Sometimes a proton is going to jump from the HBr to the water, but sometimes it's going to jump from the water H3O plus to the Br minus. And the extent to which that happens will tell us something about the strength of the acids and bases involved. We'll see that also more clearly on future slides. Okay, so in terms of the wording of conjugate acids and conjugate bases, hopefully you guys can see this now. We have sulfuric acid. After it gives up its proton, we're going to have HSO4 minus. That's the conjugate base. So they're a pair, they're both in green here. The other pair here is water, which in this case acts as a base to accept the proton, becoming H3O plus, the conjugate acid. All right, so what about for this reaction here? What is ammonia acting as? Ammonia is going to be accepting a proton from the water. So that's right, ammonia is acting as a base. All right, what word would you give to the NH4 plus after it's accepted that proton? Okay, somebody put Ca. I hope that stands for conjugate acid, and if it does, that's right. So we have our base taking a proton from the acid, and after it does that, it itself becomes an acid, the conjugate acid. Okay, what about this molecule set, this reaction set down here? Which one of these things, let's do it a different way. What would you call this green molecule here just to the right of the arrows? Think about what's the acid in this situation, what's the base, and then think about what that green thing is called. Yeah, so this green thing here is called the conjugate base, and the reason it is because typically, sort of just by custom, whatever's on the left-hand side we call the acid and the base, and then their partner pairs on the right side are called the conjugate acid. So for green matches up with green, or the I think I just said that wrong. Conjugate base, which matches up with the acid over here in green. And then of course also our blue base, after it gets that proton, will become this blue conjugate acid over here. Yeah, Kelly, it looks like you have your hand raised.
Yeah, I was just wondering, how can you tell when it has accepted a proton or not? Like, how can you visualize it?
So in the case of if I'm giving you something like this, you can visualize it because here that proton is bonded to the green molecule, and over here that same proton is now bonded to the blue molecule. Did that answer your question?
Okay, so I'm sorry. I'm so confused. The green oxygen molecule?
Yeah, so if we're looking at the bottom reaction here and we look on the left, right now that pink hydrogen is bonded to a green oxygen, right? We didn't draw it out, but there's a sigma bond between those two, and there's a lone pair above and below this oxygen, right? So this is where those chapter 1 skills come in really handy. You should be able to look at this little OH, and when you look at it, even though it's not drawn out, you should be able to see what you should visualize in your head. I don't know why it just drew a big fat line through my oxygen, but what you should be able to visualize in your head looks more like that, where you see this sigma bond written out and all the lone pairs on the oxygen. So this OH represents a bond. And then in the case of this acid-base reaction, that bond is breaking. The lone pair that are in that bond are going to go back to that oxygen. They're going to be right here now. And what moves across over to the other molecule is just a proton, because we're talking about Bronsted acids. We're all about the proton here. So this proton is going to float over here to this blue base, and the 2 electrons that are right here are going to go and make a new bond to it, and that's the bond that you see here. Did that help explain, Kelly?
Okay, yeah, it did. Thank you.
Okay, you're welcome. So what we're talking about here with acid-base chemistry, what I just went into is actually called a mechanism, more or less. I showed you exactly what's happening with all of the electrons, right? And where electrons are moving. So the electrons that were in this bond go back to that oxygen. The electrons that were on this oxygen form a new bond. Overall, what we need to be thinking about for acid-base chemistry right now is the likelihood of, is that proton going to prefer to hang out with this green acid molecule over here, or is that proton going to prefer to hang out with this blue oxygen over here? And we'll talk more about that in the slides that are coming up to determine how we figure that out. Okay, so we just talked about what acids and bases are, and we also defined conjugate acids and bases. I'm going to skip over Lewis acids and bases and come back to that topic when we cover curved arrow formalism, because it just makes more sense there. And instead, what we're going to talk about is how we can both quantitatively and qualitatively measure acidity, and therefore also think about where that equilibrium lies, to the right or to the left. Okay, first, before I get into that, I just want to take a moment and put this into perspective about why we care. Who cares? Why do we care about acids and bases? So we care about acids and bases because we're chemists, and because in chemistry land, we like to be able to think about chemical reactions, and we like to be able to define them. We like to be able to put numbers on them if we can, but we like to be able to predict them. That's a common theme that we've been talking about since day one in this course. Turns out that most chemical reactions can be treated as acid-base reactions of the Bronsted-Lowry type we've been talking about, or something called nucleophile-electrophile reactions, which I'll talk about towards the end of this chapter on Friday, that actually have to do with the Lewis acids and bases that I haven't shown you guys yet. But for these Bronsted acids and bases, we can actually mathematically make a relationship between the difference in pKa and a delta G value for a reaction occurring. So we can make a link between the measure of acidity of a compound and the delta G of a reaction that involves those proton transfers. And that turns out to be really useful. We can also use our notions here of acidity to think about reactivity. And of course, every chemist likes to be able to predict trends. I've already talked about how we like to quantify things. So in terms of acidity, we can use acidity and the pKa value, which we'll talk about in the next couple of slides, to give numbers to what we're talking about with these trends, right? Some benchmark numbers. And then finally, and then here's the more philosophical part of it, what we are going to be thinking about and talking about for really the whole semester is how molecules behave when they're interacting with each other. And so the protonation state of that molecule is important to knowing how that molecule is going to react, right? So let me see if I can get back to this slide really quick. If we look at this NH3, that NH3 is probably going to act very different in a reaction than if it were NH4 plus. And that should be intuitive. One of them's positively charged, one of them's neutral. One of them has a lone pair that is accessible and can do stuff. The other one doesn't. So the actual protonation state of different individual molecules in a reaction comes into play when we're thinking about reactions and whether reactions will occur and how they occur, which is what's defined by a mechanism, which we'll talk about later. And then finally, I just want to mention that in enzymatic catalysis, so all of the different biochemical reactions that are going on in your body right now, most of those are being catalyzed by enzymes, protein-based enzymes. And so many of those protein-based enzymes work by creating a little space, by holding the substrate or whatever in exactly the right way, that they can locally change the capability of a molecule to be deprotonated or protonated. They can make local changes to pH that influence protonation and deprotonation step and get chemistry to occur that would not occur in solution. Okay. That's not the only thing enzymes do, by the way. They do a lot of other things, but that's one of their big tricks that they have in their toolbox. All right, so let's talk about pKa, which I think is a concept that you guys have seen before in general chemistry. What pKa does is give us a way to put a number on the strength of an acid, a measure of acidity strength. And in order to get to this pKa, first we have to set up an equilibrium reaction, because all acid-base reactions are equilibrium reactions. So we're going to take a generic acid and ask about how much it dissociates in water, right? Does this equilibrium lie far to the right, where most of this HA dissociates into A- and the H+ that now is sitting on water? Or does most of this HA remain HA, and does that HA keep its proton? So in the first case, intuitively, when you push the equilibrium to this side, that is an acid that dissociates a lot, which means it's a strong acid. If you're staying over here in an HA stage, that means your acid is keeping its proton, not really wanting to give it up. That makes it a weak acid. So this is a generic reaction. We can write out a generic equilibrium constant. So that word should sound familiar to you guys from general chemistry. Equilibrium reaction, so big K. And like I said, when you have a strong acid, that strong acid is going to be mostly dissociated. So the products of this generic reaction are going to be favored, and they'll be up here in the numerator. So you'll have a very, a Ka above 1, right? In the converse way, when you have a weak acid, you're going to be favoring the reactants of your equilibrium. Your Ka will be less than 1, and the reactants will be favored. So what we can do, just like with a pH scale, we can take this equilibrium constant and we can turn it into a number that's more meaningful to us, because Kas are numbers that range from like in the hundreds or thousands to in the 10 to the -50. So it's really hard for us pea-brained humans to grasp numbers across that big of a scale. So what we need to do is to turn that Ka concept into a logarithmic scale, so it's numbers that make sense to us, that are more in our wheelhouse of like, -15 to 60, right? That sounds much easier to deal with. Okay, so in order to do that, we do the same thing that we would do to get a pH. We take our Ka, or our equilibrium constant, and we do the negative log base 10 of it to get the pKa. The lower the pKa, the stronger the acid. This is just math, so it should connect all of these concepts for you. If you have a lower pKa, right? If you have a lower pKa, then that means that your Ka is going to be greater than 1, which means your products are going to be favored, which means your acid will be mostly dissociated, right? So the lower the pKa, the stronger the acid. And we'll talk about these benchmarks, but in the next couple of slides. But water has a pKa of around 16. Acetic acid has a pKa of around 5. So you can even hear from the name, acetic acid sounds like it should be acidic, right? And it is, it's more acidic than water, so it has a lower pKa than water. You guys don't need to know this, but just conceptually, in case it helps kind of solidify concepts for you guys, the pKa is the same as the pH at which half of the compound is deprotonated. So if something has a pKa of 7 and you put it into a buffered solution at pH 7, exactly 50% of that will be protonated and 50% will be deprotonated. Okay, so this chart is directly out of your book, and it shows relative strengths of common acids that we'll see in organic chemistry. You do not need to memorize this chart. Do not memorize this chart. Do not memorize this chart. But notice a couple of things about the chart. First, notice how as you get to stronger and stronger acids, the corresponding conjugate base, so after you deprotonate a strong acid, what you end up with is a weak base, right? So the trend is opposite here and converse to each other. If you have a weak acid, and if you're able to manage deprotonating that acid, what you have then is a really strong base. And this should make sense. These strong bases are not stable. They don't want to stay the way they are. And so they're going to run around, they're strong bases, they're going to run around and try to find a proton so that they can get back to the weak acid stage. Okay. The other thing I want you to note here is that water's on this chart twice. We saw in the beginning slides that it can act as an acid or a base. Another way of saying that same thing is that it can be protonated or deprotonated. So you can see here at the top, if you are protonating water, then you'll get H3O plus. By convention, we're writing this in the direction that H3O plus is the acid that we're asking about. So the pKa of H3O plus is negative 1.7. That's actually a stronger acid. H3O plus is a stronger acid than HF, or hydrofluoric acid. And this should kind of make sense to you guys, because if you look at H3O plus, well, it's got a positive charge on it. What does it want to do but to give up a proton, get rid of that proton and go back to being a plain old stable, boring water molecule? On the other side, on the flip side, if you have water, you can deprotonate water to get OH minus, the hydroxide ion. That pKa is 16. That's actually a reasonable reaction that happens sometimes. And you can see on this scale, at least on the scale that we're looking at here, neutral water itself is kind of like in the mid-range here. Like it's a little bit on the weaker side of acids, but it's not a weak acid, right? So it still can act as an acid. When it makes its hydroxide ion, that hydroxide ion's a little bit on the stronger side of bases. So again, just notice the kind of the parallel relationship: strong acid, weak base, strong base, weak acid. Again, you won't need to memorize this chart, but I am going to ask you to know some specific benchmarks for types of molecules. And these are the benchmarks that I'm going to ask you guys to know. So I'm going to start here with carboxylic acids. These compounds, which you guys are hopefully reading on your own about the functional groups and are able to at least see the familiarity of this notation, RCOOH. What that is this functional group here that has a carbon-oxygen double bond next to an OH single bond. These molecules are a little bit more acidic than most organic molecules because that negative charge on the oxygen can be stabilized through resonance into the neighboring double bond. So that's what gives these carboxylic acids a pKa that is lower than, for example, their water and molecules like that, which are called alcohols, where when you deprotonate an alcohol or water, you have that negative charge on an oxygen. And that's good, right? Because oxygen's electronegative, so that helps. But that oxygen carrying that negative charge doesn't have the option to sometimes shift that negative charge to the other oxygen with resonance because there's only one oxygen, right? So that's reflected here in the fact that alcohols are not as strong of an acid as carboxylic acids. Now, on the opposite ends of the spectrum here, mineral acids, which you guys know and love, like HCl, HBr, those have very small pKa's. Sometimes they're negative, right? Because they're very strong acids. The X part of a mineral acid is usually something very electronegative, like chlorine minus or fluorine minus, that can handle stabilizing that negative charge because of the electronegativity inherent in it. And on the far other end of the spectrum, we're looking at hydrocarbons, so CH bonds that don't have any way to help stabilize themselves. So carbon is not electronegative, right? Carbon would be considered more electropositive in general. I know it's kind of in the middle of the periodic table, but if you're comparing it to nitrogen, oxygen, and halogens, carbon is the most electropositive of those. And those are most of organic chemistry, right? So of most of organic chemistry, carbon's one of the most electropositives. That means that if you take a proton away from a carbon, you're leaving it as a C minus, like down here with this methyl anion. That C minus is not stable. And so that hydrocarbon, before you took off that before you took off that proton, that hydrocarbon had a pKa that was huge, 40, 50, upper 30s, big numbers here. So these are the benchmarks that I want you guys to remember. And in addition to these, I'm also going to have you guys remembering some trends. So we'll be talking about how to identify trends as well. So We've just talked about pKa, quantitative measures, and I gave you guys a couple of benchmarks. We are also, just like I just said, gonna have to know how to qualitatively analyze a molecule for its acidity, which will usually be in comparison to another molecule, right? So when we're thinking about acid strength qualitatively, instead of figuring out the Ka and the pKa, because if you think about it, in order to figure out a Ka, you have to know the concentration of A minus. You have to know the concentration of HA. And then you have to do a whole bunch of math. Who wants to do that, right? So we want to be able to look at molecules and just by looking at their structure, have a sense of where do they fit in the acid-base scale of things. So the way we do this is to think about an equilibrium reaction and look at the players here and recognize that all of these, one way of thinking about this anyways, is that all of these players are fighting over one proton. And how do we figure out who's going to win? Well, that proton, all things in chemistry land and life, try to tend towards the things that are the most stable. So you want to figure out which side of the reaction gives you the more stable collection of products. And the easiest way to do this is to compare the bases of the set, right? So look at the conjugate base and look at the base itself and see which of these two things is the weaker base. A weaker base is going to be less reactive and more stable. So in the case of this example down here we have a carboxylic acid like we just talked about and an O minus base versus a conjugate base of a carboxylic acid and an OH group. So if we compare this green COO minus to this blue just O minus, like I said on the last slide, this blue base can't share that electron density with anything else. It can't spread it out. It can't let somebody else hold on to it for a little while. It's just got to hold it. And that's okay because oxygen's really electronegative, but it's not as good as the situation over here where that negative charge can be moved to the other oxygen through resonance. So I'm out of time, but I do want to say one thing really quick. I'm going to post all of the slides for today that go all the way through the acidity trends, the qualitative acidity trends. I will talk about those on Friday, but just know that I'll be posting the slides for that today so that you guys can kind of get a little preview for it. Okay, any questions?
I have a question about the practice problems.
Sure.
Are there any more that you'd recommend or just the ones up on Canvas?
So I would say start with the ones on Canvas, but the truth is all of the questions in your book are valid. Anything in the chapter is fair game. One recommendation I can make for you is that if you are trying to target a particular skill set, your book actually is really great that in the back of every chapter, it has, I think it's like a box, I think it's called problem solving skills or something like that. And it breaks down the skills that at least the authors of the book think you should know for that chapter. And then next to that skill, it tells you problems from that back set that relate specifically to that skill. So in chapter 1, if you wanted to practice doing resonance drawings, finding resonance structures, you could look in the back of the book, find where it says resonance, and then look to those questions. Did that help?
Yes, thank you.
And just a reminder today, we do not have office hours today. I've readjusted them to Thursday and Friday this week so that you guys have a chance to take a look at your quiz scores when I post them. Probably tomorrow morning is when I'll post your quiz scores. And then I'll be available in the afternoon tomorrow and on Friday. And the times are on my first slide. So when I post them, you'll be able to see that. So, okay. Anybody else? No? All right. Thank you guys. I will see you on Friday. I hope everybody gets...
Professor, okay. I'll wait.
No, go ahead. I was just saying I hope everyone gets some sunshine. Go ahead, Jessica.
Professor, I'm so sorry. I missed Monday's class and I missed my quiz.
The quiz was on Friday of last week.
Oh, Friday, yeah.
Yeah, so there's no makeup quizzes according to the syllabus. So if you've missed a quiz, that's gonna be the quiz that gets dropped for your grade.
Okay.
There's the slides for class were posted for Friday and then also for Monday, so you can review the slides.
Yeah, and I'll submit my my in-class interaction.
I don't think we had an in-class participation for Friday or for Monday.
Okay. Because the other one got graded. I noticed.
Yeah. We've only had 2 so far, and so as long as you have both of those in, then hopefully you're counted already. Okay.
No problem. Thank you.
You're welcome.